So now we're going to look at the relationship between the energy changes in a reaction and the kinetics of the reaction. So what you're looking at here, let me go full screen here with this. What you're looking at here are what we call in the business energy diagrams, or in some textbooks, they call it the energy profile diagram. And in each case, what you have is a plot of the potential energy on the y-axis versus the reaction progress on the x-axis. Now here we have two diagrams, two such diagrams, one for an exothermic reaction and the other for an endothermic reaction. And you'll notice that in each case, when you start off with the reactants A and B, they need some energy in order to get up to this point here. The same thing is true up to this point here. And therefore you have a combination of those two reactants, which is called the reaction complex. And you'll notice that it has a certain amount of energy relative to the reactants that you start off with, which is labeled as EA, right? That EA is called the activation energy, and it represents the minimum energy that is needed by the reactants in order for the reaction to take place, right? So what this means is that if the reactants do not have that minimum energy, then the reaction will simply not take place, and the reactants will basically reform in their original phases, all right? Now, assuming that they have enough reactants or enough energy in the reactants to overcome the activation energy, then what will happen is that the energy will start to fall and you get to your products. Same thing happens over here, but you'll notice that the difference between this and this is that the energy of the products here is less than the energy of the reactants, which is what happens in the case of an exothermic reaction. And in this case, the energy of the products is greater than the energy of the reactants, which is what happens in the case of an endothermic reaction, all right? So as we said before, the activation energy is what I defined here as the minimum energy that is needed by the reactants in order for the chemical reaction to be initiated. Now, based on other experiments, we can see, and which is actually based on what we have just discussed here, you can see that there's actually a relationship between the rate constant of a reaction and the temperature, all right? And basically, you see here it increases. And there's a mathematical equation which describes that line, which is given right here. K is equal to A times e to the minus minus EA divided by RT. And this is known as the Arrhenius equation, all right? So just to define the terms, EA is the activation energy. Its units is in joules per mole. R is a molar gas constant, which we are familiar with. However, the value that we should use is this one right here in order to keep everything consistent. T is the temperature in Kelvin, and A is a factor known as the frequency factor. It's a measure of the tendency of the molecules that are reacting to basically contact each other, impact each other in the right way, in the correct orientation, and the correct energy, all right? So that's called a frequency factor. Now, we can also express this same equation in this form, right? I won't go through the steps. This is something you should be able to do from your algebra experience, but in this form, it's very useful because if you look at this form carefully, you'll see that this equation is in the form of y. Let me write it down here. The straight line equation y is equal to mx plus c, right? So c would be the ln A, x would be the 1 over t, m would be minus EA over r, and y would be the ln k, right? So basically the two variables that you'll be looking at is ln k versus x. And if we do that plot, you're going to get this relationship, this graph, this straight line right here. As you can see, it has a negative slope, which of course indicates that is indicated in the equation. I'm sorry, let me go back to the pointer function. It is indicated in the equation where you have a negative sign, so it comes as no surprise that we have a negative slope. So therefore, the slope would be equal to minus EA over R. ln K, of course, is the y-axis, 1 over t is the x-axis, and ln A is basically the intercept on the y-axis, all right? So this graph is very useful. This form of the equation and the plot is very useful because you can use it to determine the activation energy of the reaction and also the frequency factor, all right? Okay, so this is basically just showing you an example of a reaction between potassium and a compound known as iodomethane. And what this is underscoring is what I was talking about earlier with respect to the molecules oriented correctly so that a reaction can take place. So as you can see here, the potassium atom is coming into close proximity to the methyl iodide. Now, just to show you or tell you what the different colors, colored spheres represent, this here is the iodine atom, I should say. This, of course, is potassium. And the black sphere represents carbon. And the three white spheres here represents hydrogen, right? So when the molecule of methyl iodide is oriented this way, then it is easy for the iodine to be transferred to the potassium. So that illustrates the correct orientation for the reaction to take place. On the other hand, if the iodomethane molecule is oriented this way, then of course it does not allow for the easy transfer of the iodine to the potassium, and therefore no products are formed. All right. So that is one important factor that one has to consider when examining how fast a reaction goes. You have to conceive and think about the possibility of the molecules that are reacting orienting in the correct way such that the reaction will take place. Okay, I'm going to stop here. So the next topic we're going to look at is reaction mechanisms.